I'm Jyoti Sharma, once again in front of you to give you some lectures on electrical machines, which is the fourth unit of basic electrical engineering, which is having the subject code of KW101 according to AKTU. Moving on to the next of the lecture, this is the third lecture of mine. Earlier we have discussed DC generators, their construction, their classifications, how they work. The last classification which was remaining for the compound generator, that was cumulative and differential compound generator. We are going to discuss this for the very first thing what we are going to do. Then the applications of the various DC generators what we have discussed earlier. Then we'll be starting with the DC motor. So its working principle, then what is this back EMF, what is its significance, then the torque equation for DC motor, and then the types of DC motors. Okay, now coming to cumulative and differential compound generator. So if you just see, we have seen that a compound generator is the one which is having a series field winding also and a shunt field winding being wound on the pole core, right? Now, a cumulative compound generator is the one, it can be seen in the very first diagram, that here, the series field winding and the shunt field winding, both of these are connected in such a fashion that if at all I say the current flowing is in this direction, right? So, obviously the flux produced according to the right hand thumb rule, right? So, the flux produced would be in the upward direction by the series field winding, right? Similarly, for the shunt field winding, it is also having the same direction. So, the flux produced will also be once again in the same direction, right? So, both of the fluxes are supporting each other. Both of the fluxes are supporting each other. It means that the net flux would be an increased flux, right? So, or a cumulative flux. That's why we used to call it as a cumulative compound generator, right? Whereas, if you just see the another figure, that is for a differential one. In this case, the direction for the series, that is reversed. That means obviously the flux produced would be in the opposite direction, that is say phi SC, right? And the flux produced by the shunt field winding, that will be in the upward direction. That means the net flux produced by the generator would be the difference of the two. Both of them will not be supporting each other. The net flux would be the difference of the two. So, the flux would be always be decreasing, right? Let the excitation be increased. The flux will not be increasing because every time you will be getting the difference of the two fluxes. That's why it is being called as differential compound generator, right? So, coming to the applications of the DC generators, the various DC generators what we have seen. So, the applications, if at all I say, the application for a separately excited DC generator, it is used for power and lighting purposes, right? The series DC generator, that is used in arc lamps for lighting stable, and it is also being used as a stable current generator and booster. DC generators, these are used to immerse the voltage drop within the feeders, and these are also used to provide a power supply for say hotels, for hostels, for lodges, offices, etc. Coming to DC motor, right? We have seen the working principle for a DC generator. Now coming to a DC motor, constructionally there is no difference between a DC generator and a motor. The difference which comes over is with the working principle, right? So, a DC motor is a device which converts the direct current into the mechanical work. It works on the principle of the Lorentz law, which states that the current carrying conductor placed in a magnetic or electric field will experience a force, and that force is being called as Lorentz force. The direction would be given by the Fleming's left-hand rule, right? Now, what is this Fleming's left-hand rule? We all know that all of you must have studied in year 12, that if the thumb, the middle finger and the index finger, right, of the left hand are displaced from each other by an angle of 90 degree, then the middle finger represents the direction of the current. The index finger will represent the direction of the magnetic field, and the thumb will show the direction of the forces acting on the conductor, right? So according to that, we can be seeing the working principle of the DC motor. The formula that calculates the magnitude of this force is being given by BIL Newton, where B is the magnetic flux density, I is the current in the conductor, and L is the active length of the conductor, right? Now, if for a simplicity, if you just consider that the armature has only one coil, right, which is placed between the magnetic field as is being shown in the figure. These are the magnets. North to south is the magnetic field, and in between that I have placed the conductor, right? So when the DC supply is being given to the armature coil, the current starts flowing through it. So this current develops their own field around the coil, right? This figure, this shows you the field being created by the conductor itself. Right here it's dot and here it's cross, right? So according to that, the field created by this would be, obviously, if you just see here, this is inward, this is outward, right? So it will be like this and it will be like this, right? So I'll be having the field being created by the current carrying conductor, right? Now, by the interaction of the fields, right, which are the two fields? One is the field produced by the coil and another is the one which is produced by the magnets. So the interaction of these two fields will result in the resultant field which develops across the conductor, right? This is the resultant field. Towards this side, if you just see, towards the downside, the main field direction is, say, downward from north to south, right? And the direction of the field created by the current carrying conductor, that is upward towards this side. So here there will be a cancelling of the field, and towards the other side, both of these are in fact towards this side, it is both of these are supporting, right? So both of these are supporting. This is towards this side, downward side, the strength of the field would be more, right? Where on the upward side, if you just see, the direction of the field created by the current carrying conductor is towards the left and the main field is towards the right. So in that case, both the fluxes will cancel out each other. So here I'll be having a minimum density of flux, right? So this acts like a stretched rubber band, you know. If you just stretch it over towards your side, the paper which you are having, you know, that will be pushing towards the lower force side. The same thing happens with the conductor as well, right here. So I'm having the maximum flux being created over here, and this side I don't have, or I may be saying a minimum amount of flux at this area. So the force would be exerted towards this side, towards the conductor. The same thing happens for the conductor over here. This is cross convention. So this time, this is feeling the force towards downward direction. So I must be saying that the resultant field tends to regain its original position, that is in the axis of the main field, and the field exerts the force at the ends of the conductor, and thus the coil starts rotating, right? Now, while doing this, we have got the motoring action, right? When the force is being exerted on the conductor, you know, the conductor will start to rotate, or the coil will start to rotate, right? So that the motoring action is being achieved, right? Now, after the motoring action, if at all I say, every motoring action is now, especially in a DC motor, the motoring action is now followed by a generating action, which gives result to a back EMF. Now, what is that? So, when the armature of the DC motor rotates, which we have seen in the earlier slide, the winding or the conductors on the armature, they also rotate in the magnetic field. The magnetic field is there. We have excited it. It is present, right? So, after the motoring action, obviously the conductors are also moving. Now, according to Faraday's law of electromagnetic induction, the EMF is induced in the conductors, whose direction, as found by the Fleming's right-hand rule, is in the opposition to the applied voltage, right? And that can be given by the Lenz's law as well, you know, that every induced EMF will oppose the very cause producing it. In case of DC motor, the EMF, which is what we are getting, the induced EMF, that is because of the applied voltage, right? So the EMF induced in the armature winding is in the opposite direction, hence it is referred to as back EMF or EB of the motor, right? The back EMF, it tries to oppose the applied voltage, but it has to drive the armature current IA against the opposing of the back EMF, EB. That's why if you just see, the armature current is given by the net voltage by the resistance. What is the net voltage we are having over here? Obviously, that is the supplied voltage minus the back EMF. Back EMF, the generated EMF, although it is having the same formula as well as the same value as that what we used to get as the generated EMF, which is given by phi P N Z by 60A, what we have derived in case of DC generator, the EMF, right? Where phi gives the flux per pole, P is the number of poles of the motor, speed is the speed of the armature, this is the total number of conductors, A is the number of parallel paths depending upon which kind of winding is there in the armature, right? So it is given by V minus EB upon RA. RA is the armature resistance. Now, the important thing is this back EMF that depends upon the armature speed, right? It is having the relation what we have seen in the earlier case, phi P N Z by 60A. If the speed is higher, then the back EMF is also high, and hence IA is small. If speed is less, then EB is also less, hence the more current flows to develop the required torque, right? We'll be once again discussing this regarding to the regulating mechanism of back EMF. Now, what is its significance? Do we really require this generating action to be there after the motoring action, right? So, the very first thing is what is its significance? So, the very first significance of it is, as the back EMF, it opposes the supply voltage. Therefore, the supply voltage has to force the current through the armature against this back EMF to keep the armature rotating. So, this electric work done in overcoming and causing the current to flow against the back EMF is converted into the mechanical energy developed in the armature. So, that means it follows, therefore, that the energy conversion in a DC motor is only possible due to the production of the back EMF, okay? And second, the mechanical power developed in the armature that can be given by the back EMF, that is EB, multiplied by the armature current, right? The second significance, now the back EMF makes the DC motor a self-regulating motor. That is, the back EMF makes the motor to adjust the armature current automatically as per the load torque requirement. So, we can be seeing that, right? So, as we know that the armature current is given by V minus EB upon RA, right? So, where V and RA are fixed. So, therefore, the armature current IA depends upon the back EMF, right? Which in turn depends upon the speed of the motor although, right? So, if the motor is running at no load, that means the small torque, right? So, the torque that is equals to or that is proportional to armature current is required by the motor to overcome the friction and windage losses, okay? So, therefore, a small current is drawn by the motor armature and the back EMF is almost equal to the supply voltage, right? Now, if the motor is suddenly loaded, right, then the load torque becomes greater than the armature torque and the motor starts to slow down. As the motor speed decreases, the back EMF also decreases and therefore the armature current starts increases. We have seen the relationship, right? They are inversely proportional. We have seen the relation that armature current is given by V minus EB upon RA, right? So, what we are saying that with the sudden increase in the load, the motor speed is going to obviously decrease. With that, the back EMF, because that is directly proportional to the speed, the back EMF is also going to decrease and therefore the armature current, it starts increasing. With the increase in the armature current, the armature torque increases, right? It's directly proportional. And at some point, it becomes equal to the load torque. And at that moment, the motor stops slowing down and keeps running at that new speed, which is according to the new load, increased load demand, right? Now, if the load on the motor is suddenly reduced, the opposite happens. Then the driving torque becomes more than the load torque and the motor starts accelerating. How much it should accelerate, right? Should it reach the infinity? No, that is being regulated by the back EMF. How? As the motor speed increases, the back EMF also increases and therefore the armature current now decreases. So, due to this reducing armature current and the armature that developed torque that is also decreased and at some point it becomes equals to the load torque. At this point onwards, the motor will stop accelerating and will start rotate uniformly at this new lightly increased speed. So this shows how important the back EMF in DC motor. Without back EMF, the electromagnetic energy conversion will not be possible, right? Okay, coming to the very important topic, that is the torque equation. As we have seen for the DC generator, the generated EMF that can be given by phi p and z by 60A. But in case of DC motor, the output is the rotation or the torque with the help of back EMF always. Back EMF is once again given by the expression. It is nothing but the generated EMF although. So it is also given by the same expression. But what about the torque for a DC motor? So if we just see, when the armature conductors of a DC motor that carry current in presence of a stator field flux, a mechanical torque is developed between the armature and the stator. The torque is given by the product of the force and the radius at which this force acts. Obviously, the torque is given by force into the radius of the armature, right? Work done by this force in one revolution is given by force into the distance. So that is F into the distance is obviously the circumference of the armature, that is 2 pi r. So the net power developed in the armature, that is work done by time. Once again, work done we have calculated, that is F into 2 pi r into number of revolutions divided by the time, right? So that is F into 2 pi r into N by 60, that much joules per second, right? But we also know that F into r gives us what? That is the torque. And 2 pi N by 60, that is nothing but the angular velocity omega in radians per second. So putting these in the above equation, I may be saying that the power developed in the armature is given by P is equals to the torque multiplied by the angular velocity omega joules per second. So just put it in the DC motor scenario. If at all I just say that tau A is the armature torque. It is the power developed. Now the power developed in the armature can be given as we have just seen. PA is the power developed in the armature, that is given by the armature torque multiplied by the angular speed, just substituting for that. The mechanical power developed in the armature is converted into electrical power. So the mechanical power is equals to electrical. That means tau A into 2 pi N by 60, that must be equals to the mechanical power given by, we have derived it in the earlier slide, that is back EMF multiplied by the armature current. We also know that, how do we give the expression for back EMF? Obviously, phi p and z by 60A. So just substituting for all those, tau A into 2 pi N by 60, phi p and z by 60A into armature current, rearranging, right? So we'll be having the expression for the torque can be given as Pz by 2 pi A into phi into Ia Newton meters, right? So this term Pz by 2 pi A is practically constant for a DC machine. So the armature torque is directly proportional to the product of the flux and the armature current. This is very important as we will move on for the characteristics of DC motor, right? So when we'll be moving on to the characteristics of DC motor, we will be studying how does the motor behaves when, you know, there will be a comparison between how what will be its characteristics for a torque versus armature current, torque versus speed and all that. So for that we'll be requiring this relation, right? Now coming to the types of DC motor, this is very much similar to what we have done for a DC generator, right? Likewise for a DC generator, we were having separately excited DC generator. Likewise, we used to have a separately excited DC motor. Conceptually, it's the same as the name signifies. The field coils or the field windings are energized by a separate DC source, right? So what are the relations? Now once again, so here it can be seen the field is being supplied from a different DC supply, and also because this is a DC motor, I must be saying it is being fed. A separately excited DC motor is a doubly excited system. We are going to excite the field as well. We are going to excite the armature as well, right? We are going to give a DC supply to the armature, right? So that I'm having the line current getting in. The armature current is also getting in the armature, giving me the back EMF with the armature resistance Ia. So obviously RA. So I'll be having a drop of IARA as the armature resistance drop over here, right? So the relations, the current relations holds good. Likewise, I can see here the line current is equals to the armature current, right? And what about the voltage equation? So now it is just reversed for a generator and for a motor. So now I'm having the input voltage, input supply as V, the back EMF is EB over here. So if at all I just apply my KVL in this, I'll be having the expression as V would be given as the back EMF EB plus the drops. What are the drops I'm having? Obviously the armature resistance drop IARA plus the armature reaction, what we are not considering right now, plus the V brush. That means the brush contact drop, what we have discussed in generators as well, right? Now, self-excited DC motor. Now, in case of self-excited, we have discussed, obviously, once again, I can be having various classifications. I can be having shunt, series, compound. Now, I'm directly coming, you know what does a self-excited means. In this type of motor, the current in the windings is supplied by the machine or the motor itself, right? So, for a shunt wound motor, this is the most common type of the DC motor. Here, the field winding is connected in parallel with the armature, shunt with the armature, right? Now, so what are the relations? Once again, it's the same. I'm giving a DC supply to the armature. The same supply is being fed to the shunt field also, but the shunt field is having a higher resistance of RSH, so that there is a very minimum current which is flowing in it. That is given by ISH. This is the line current taken in by the motor. Obviously, the armature current. So here, the relationship for the currents, that is holding good as IL must be equals to IA plus ISH. I can apply my KCL at this point, right? Similarly, for the shunt field winding, if at all I see, the voltage across the shunt field winding is given by V. So that is given by ISH into RSH, or obviously, ISH is given by V upon RSH. The voltage equations, right? Once again, there is no change in the voltage equations if you just see, right? I'm having the same KVL loop, what I was having for a separately excited one, right? So once again, V is given by the back EMF plus the armature resistance drop plus the voltage brush contact drop. Now for a series wound motor, right? In this motor, the field winding is connected in series with the armature winding. The connection diagram is shown over here. In this case, obviously, the windings is connected in series with the armature, right? This is the supply being given. In this case, if you just see, this is the line current, the ISC, the series field winding current, and the armature current. All the three are the same. I'm having the same loop, right? So all of the three are the same. IL is equals to ISC is equals to IA. Voltage equation, I'll be having a small change. What is that change? Now I'm having a one more drop being added to it. What is that drop? That is the series field drop. That is V must be equals to EB plus IARA plus ISC RSC. But obviously ISC is equals to IA. So that's why IA I have taken as common. So that is RA plus RSC plus V brush, right? Now coming to compound, we know for a compound motor, right, likewise in a generator, the field winding would be connected in series as well and in shunt as well. Depending upon the constructional difference, I may be having a long shunt DC compound generator, a motor, or a short shunt. What used to happen for a long shunt? Obviously, the shunt branch is connected in parallel with the armature as well as the series field winding, right? So both of these used to be in series and the shunt field winding used to be exactly in parallel with that, right? Because of this kind of construction, once again, the relations, the current relations, this is the line current, then the series field current, then the armature current and the shunt field. Once again, your voltage, that is completely across the shunt field. So I may even write here that ISH is equals to the voltage across the shunt field winding is V upon RSH, right? Relations about the current, obviously IL must be equals to, if at all I just apply IA plus ISH. Also, where is ISC then? It is not in the picture. Yeah, it is. This IA is equals to ISC. Voltage equations, it's the same as that for a series one. There is no change. If you just see, the loop is the same. The KVL if at all I apply my KVL to this loop, it is going to be same. V is equals to the losses IARA plus ISC-RSC plus back EMF plus the brush contact drop, right? Now, in case of short shunt, right, the only difference it is making is, in case of short shunt, the shunt branch that is in parallel only across the armature, right? So, in this case, the series field winding or the series field drop is with the same polarity as that for a, I must be saying it is in opposition with the V, right? That means V minus ISC-RSC must be equals to the voltage drop across the armature. Once again, the current relations, if at all broadly I say, current relation is the same. IL is equals to IA plus ISH. But this time, likewise for a long shunt, that there IA is equals to ISC. But now I can't, can I say that I is equals to ISC? No, no. So now I is not equals to ISC. Then IL is equals to ISC, right? My line current is equals to the series field winding current. The voltage equation, that is going to remain same. The mesh is the same. The back EMF, what I am having over here, plus the armature resistance drop IARA plus ISC-RSC plus V brush, right? Now, how to give the expression for ISH? In earlier case, it has to be V minus RSH. Can I say the same over here? Can I say the voltage across the shunt field winding is V? No. What is the voltage across the shunt field winding? It is V minus this drop. What is that? ISC into RSC. I may write in terms of the back EMF as well, right? That may even be given as back EMF plus IARA plus V brush upon RSH, right? Both the ways. Now, coming to the characteristics of DC motor. So, generally the three characteristics curves are considered important for a DC motor, which are first one, the torque versus armature current, the speed versus armature current, and the speed versus torque. So, these are explained in the next of the slides. These characteristics are being determined by keeping the two relations in mind, which I have just told you, right? One is with the torque. We have just derived that the torque is proportional to flux into IA and the speed is proportional to back EMF by flux. This is what we have gotten from the expression for the back EMF, right? According to these equations, we'll be going with the characteristics of a DC motor. Now, coming for a DC series motor, if you just see. Now, in case of DC series motor, the very first characteristics what we are going to see is the torque versus armature current, right? So, it can be seen over here, no? The torque is directly proportional to flux into IA. We know that. Fine, right? In case of a DC series motor, this flux is proportional to what? This flux is not constant. Likewise, in a DC shunt, we'll be discussing that, right? It's not constant, but the flux is proportional to armature current as well, isn't it? So, flux is because of the armature current, all the three currents are same. IA is equals to IL is equals to ISC, right? So, the torque is proportional, the flux is proportional to armature current. That's why the torque is proportional to armature current square. So, the graph what you got is this, right? This is the armature torque and this is the shaft torque, right? Obviously, the shaft torque is the torque which is available at the shaft, which is lesser than the armature torque because of the stray losses, you used to have a lesser amount of shaft torque available at the shaft compared to the armature torque, right? Then the speed versus armature current. What is the relationship? Now, if you just see, speed is proportional to back EMF by flux. How do you give the expression for the back EMF? That is being given by V minus IARA minus ISC-RSC, V brush I am neglecting, right? Upon flux, where flux is nothing but, flux is proportional to armature current only, right? Now, if we just increase the armature current, right? If the armature current is increased, ISC is also equal to that. If the armature current is increased, this drop is going to get increased. That means V minus IARA and all these drops should be decreased, right? But as you know, the value of the armature resistance and the series field winding resistance are not very much higher, These are very small values. So these drops are not very much significant compared to the constant voltage, right? So these drops are not very much significant. So there will not be a much decrease in this voltage. It is going to remain almost constant. It is going to remain almost constant as that of V. It is going to remain as that of V. So because of that, right? So the relation what we were getting is the speed proportional to V upon flux, right? V is almost constant, flux is armature current, so it is inversely proportional. So the speed is inversely proportional to the armature current. So the graph we have got is inversely proportional. Now the torque versus speed, this is the last graph what we can have from the earlier two one, right? We know the relationship between speed versus armature current. What is that? The speed is inversely proportional to armature current. We also know how the armature current and the torque, armature torque are related. We know that the torque is proportional to the armature square. So how I can substitute that? Can't I write it as 1 upon under root of torque A? Armature torque, right? So obviously it's inversely proportional to under root of it. So the nature of the graph is going to remain the same, right? So these are the three graphs for a DC series motor. Now, there is a very important question which is there, which says why DC series motor should never be started on no load. So we know the relation that the speed is proportional to back EMF by flux, right? So for a small load current, the change in the back EMF EB is small and it may be neglected. Hence, for a small current, speed is inversely proportional to flux. As we know, the flux is directly proportional to the armature current. The speed is inversely proportional to armature current. Therefore, when the armature current is very small, the speed becomes dangerously high. That is why a DC series motor should never be started without some mechanical load. But at heavy loads, the armature current IA is large and hence the speed is low, which results in decreased back EMF. Due to decreased back EMF, more armature current is allowed, right? Now the characteristics for a DC shunt motor, right? Now in this case, now the torque and armature current, the relationship is the same. Torque is proportional to phi IA. But in case of a DC shunt motor, we know that the flux is constant. The flux is proportional to the current flowing in the field winding, that is ISH, and that is given by V upon RSH. Both of these are constant, so the flux is also constant, right? So if the flux is constant, torque is directly proportional to armature current. That's why a straight line shunt, the shaft torque, that is slightly lesser than, so that is behind the armature torque, right? Now, with the speed versus armature current, now the relationship is speed is proportional to back EMF by flux, but once again flux is constant. I'm not writing that. Back EMF is given by V minus IARA, V brush, negligible, right? Now, once again, V minus IARA, whatever may be the increase in the armature current, let it be from no load to full load, right? The armature resistance is very small. That's why this value is not going to be very much significant, right? If that drop is not very much higher, obviously V minus IARA, this drop is not going to be very much lesser, So the back EMF is not going to decrease much. So the speed is also not going to decrease much. So if this is the base speed, what is being given by the straight red line, then with the increase in the armature current, I'll be having a small drooping characteristics so it gives you a fairly constant speed, right? That is the characteristics of a DC shunt motor. It gives us a fairly constant speed. The same is with the last, that is speed versus torque. As we have seen in case of series, the last one can be derived from the earlier two ones. Speed is how it is related. Speed is proportional to back EMF. We have seen in the earlier case, right, with armature current, or we have seen that the speed is here, it is going to decrease a bit by a small amount with the increase in the armature current. It is inversely proportional, right? Now, here also, because, what happens with this torque and the armature current, right? These two are directly proportional. So here, in fact of armature current, I may be just substituting torque. So it is going to be, the nature of the graph is going to remain the same, right? So I'm getting the same kind of graph as we have got in the earlier case, right? Now, the characteristics of DC compound motor, cumulative and differential, right? For that, we require all the four on the same plot, just to understand this, right? Okay, so for this, if you just see, here, this is torque versus armature current. The first one, it is the graph for the series. It gives us the highest starting torque because the torque is proportional to the armature current square. The shunt, it is directly proportional, so it is lagging behind. Cumulative, we know that the cumulative motor is having the characteristics of the shunt as well as series. So obviously, this is having most of its characteristics lying in between the series and shunt, right? So the cumulative will be having its characteristics lying between series and shunt. The differential, you know that for a differential, the property is the flux will always be weakening. So if the flux is weakening, it is proportional to the armature current, or let it be proportional to the ISH. In both the cases, right, the torque is not going to get increased much because the flux is not increasing. We know that the torque is proportional to flux, isn't it? Torque is proportional to flux IA. So the flux is not very much increasing, so the torque is not very much adding up, right? So it is having its characteristics at the below, right? The second one, we can see this is the constant baseline. For the series, it is inversely proportional, dotted, right? For the shunt, it has a small drooping characteristics. We have seen cumulative, once again, will be lying between the shunt and the series. Differential, you know, the speed is inversely proportional to the flux. And in case of a differential, the flux is never increasing, you know. So flux is decreasing in any of the case, so the speed would be increasing. So this is the motor which gives you a characteristics which is not desired by any motor. We know that when the load is increasing, when the armature current is increasing, the speed has to decrease, right? Either by a small amount or by a higher amount, but it has to decrease. But in case of differential, it shows a reverse characteristics. With the increase in the load, the speed also increases. The same kind of graph would be given for the speed versus torque as well, right? In next of the lectures, we'll be discussing the applications of these motors and certain numericals on these motor. Thank you all.